When we talk about the shapes of a molecule and the fact that it is whether a polar molecule or a nonpolar molecule, which is different than talking about whether it has a polar bond or nonpolar bonds, we're going to use that to reason why things happen in later chapters. So I will draw a molecule at one point in time later, and then I will talk about how that molecule interacts, but you need to be able to put it in three-dimensional structure, determine if it is polar, to reason why what we're going to see happen in real life. So this concept is very important to be able to rationalize and understand why things are the way they do, because from this point on, we will talk about molecules interacting, but this is the reason why your body functions, how things in the body interact and why things come together, bind, and cause a function inside your body. And so this concept is pretty fundamental. All right, we're going to turn our attention in Unit 7 to calculations. Oh, I just want to let you know I did re-lecture that part on hybridization and posted it up on the website so that if Dr. Hearn's perspective was something that was a little bit, oh, how does he teach? I went ahead and put on that same lecture for you to take a look at. So between the two of us, maybe you can understand what's going on. Unit 7 really kind of backtracks, and what we're going to do is we're going to do lots and lots of conversions. But what we're going to do in terms of conversions, we're going to associate it to chemical reactions, because ultimately that's what we're interested in. Put two things together. What happens? Does it explode? Does it bubble? Does it do something? And then quantify what's going to happen. And that's what we're going to look at with these. So we're going to talk about equations themselves, the chemical story. We're going to talk about how we measure things, moles, molecular mass, empirical formulas. We're going to do some stoichiometry. And then the ultimate, we're going to all put it together in one culminating problem called a limiting reagent problem, which we practice every single item in this chapter, all in one question. You know, that's how we like to do it. One question that answers everything. So a chemical reaction is this. You start off with at least two things, and you mix them together. Sometimes they will rearrange and recombine to form something different. Sometimes you mix them and nothing happens. That's not fun. But when we mix them and something happens, we get a chemical reaction. The items that we started with have different properties than the products that we produce. And so we will start with reactants, the things that are going to react, and we'll end up with products. We'll describe this using a chemical equation. Now, how in the world do you know if a chemical equation has occurred? Most of the time, a chemical reaction has occurred if there is a change in the energy. And the change in energy could be heat or light, right? And if we're talking about energy, for us, the instrument that we use to determine if something is happening is a thermometer. We're looking at temperature, the movement of temperature, which is a movement of energy. We have two terms, exothermic and endothermic. Thermic refers to heat, the movement of heat, like a thermometer. We're metering the heat. Exo means out, endo means in. So an exothermic reaction, energy is released. If you held it in your hand and energy is released, it would feel hot. Endothermic, energy is absorbed. So if you put something in your hand and it was endothermic, it would take the energy from your hand into itself. It would feel cold. Most reactions will be exothermic if they are what is called spontaneous. You can also see a color change. That is an indicator that reactions are occurring. Now, you can have color changes that aren't, but color changes usually indicate a reaction. We can form a precipitate, meaning two liquids that were perfectly clear and dissolved. If you mix them together and after they're mixed together you get a cloudy substance or a solid, a precipitate, that is a reaction that occurs. And the last, if you produce gas, you've done a reaction. So these are indicators of a reaction that's occurred. Now, to tell a chemical story, we start off like all good stories, once upon a time, okay, and then we'll end happily ever after. Now, the once upon a time is the products that come to, the reactants that come together, the things that are going to react. Then the arrow indicates something happens. Okay, the story happens, but happily ever after are the products that are formed. And so, the chemicals you start with, reactants. The chemicals you have at the end, products. An example I show below is saying this chemical story. 2 sodium, and this is the element because there's only one capital letter, and one that is in the solid form because the sodium metal is a solid, okay, will yield 2 water molecules that are in the L state, liquid state. And if I take those 2 things, I plop a solid chunk of sodium into liquid water, it'll produce 2, what is this compound? Sodium hydroxide. Oh, you're going to have to name compounds from now until forever. That is an AQ, an aqueous state, meaning that it's been dissolved. And hydrogen, the element, and hydrogen is a gas. And so my reaction has proceeded. Now, 2 things that drive this reaction, the reason why. Remember, I said if you form a gas, a reaction occurs. Okay, that's one thing. Also, this will give off lots of heat. It's exothermic. 2 indicators that a reaction has occurred. All right, and I have to have 2 sodiums with 2 waters to make 2 sodium hydroxides and 1 hydrogen gas. Now, chemical formulas, we've looked at this a little bit before. The subscript indicates how many atoms are there, and you know where that subscript came from. Hydrogen is a plus, oxygen is a 2-. The reason why there is a 2 at the bottom is because if I put 1 and 1 together, it doesn't balance. I have to do crisscross to get H2O. That is where the subscripts come from, the inherent stabilities of the 2 things that react. You don't get to change those just willy-nilly. Okay, it all depends upon how they react. But you can put in front of anything a coefficient, which tells you how many are there. And so I can say there are 2 there, or 3 are there, or 4 there. I can tell you all sorts of things that are there, but it just represents that there are multiples. If by chance you just put and change the bottom numbers, okay, you change the element, and you can see how the molecules are bound differently, and the different arrangement creates a different compound with a host of different properties. I can drink water. I can drink hydrogen peroxide, but should you? No, okay? The reaction is totally different. Now, when I look at this, how many bariums are represented in that? 1. How many oxygens are represented in that? 2. And how many hydrogens? You have to distribute that 2 across everything inside the parentheses when you're counting. So subscripts come from the type of reaction, the 2 elements coming together. Coefficients are those that we can change, but it tells you how many of each you have. In a chemical reaction, we name the compounds and the elements that react together, and we put beside it an indicator of the state of the matter. Now, there are 3 states, solid, liquids, and gases, that you know of, And we have one other state that we're going to call aqueous, AQ, okay, to indicate that that molecule has been dissolved by water. And so aqueous is going to be a case. Now, a solid can be in two ways. It can be a solid chunk that you start off with and you react it. Also, if you create solids from liquid states, so two clear liquids, and it becomes solid, that solid's called a precipitate. So if you have two aqueous things, put it together, the arrow occurs, and on the other end, you get a solid. That meant it was a precipitate. So it's a very specific type of solid. All right, but you can indicate solids for both. The chemical reaction itself is an arrow saying something is happening. The chemical arrow can tell us a couple more things. If there is something needed, like it takes place in acetone or it takes place in ethanol, okay, we'll write that on the top. If it takes place in water, for general chemistry, that's what we assume. We don't have to put water there. You can articulate it, but we assume everything's happening in water in general chemistry. We also quite often need to heat, and so you can write heat above it, but we also use this, the delta symbol. If you ever see the delta symbol above, that meant we heated the reactants to produce the products. So that's something you may see different. We also have different arrows. One arrow says all of the reactants went to all products. Okay, it goes in one direction. But chemical reactions don't always go in one direction. Sometimes they go to the right and produce products, and then sometimes the products break back down into the reactants. And you can get what's called an equilibrium, where they're going back and forth, but you reach a place where the concentrations on each side become constant. And so you can see a double arrow written in different ways to show that the reactions go back and forth. And if you see two reactants, an arrow, and NR, that meant no reaction happened. I just mixed them together, but nothing happened. Now, to govern reactions and to tell a true chemical story, we have to talk about the law of conservation of mass. The law of conservation of mass, in particular to chemistry, came about because people thought about chemistry as being weird, and they didn't have a good idea about this. And it came from a very simple reaction that occurs, and that is burning wood. Has anybody have a real wood burning fireplace in their home? Anybody? Okay. And so, yeah, so you've seen it, right? And I had to, at one point in time in one home that I lived in, we heated our house with that. And so we would get logs, and the logs weighed quite a bit, right? You put the log in, and you light it on fire, and you get heat. And I had the duty of cleaning out the ashes. When I cleaned out the ashes, did the ashes weigh exactly the same as the log? Did it weigh more or less? A whole lot less. For a long, long time, people thought that the wood that was burnt was destroyed. Okay? That was what it seemed like. Started heavy, finished light. So it must have been destroyed in the reaction. But when we really looked at this, and if we took a log and put oxygen inside a box, and we measured the entire box with the oxygen and the log at the beginning, and then we burnt the log, let it burn completely, and there's just a little bit of ash. If you take that same box that was sealed and you put it on a balance again, what do you think would happen to the weight? It weighs the same. It absolutely weighs the same. Now, what happens to the log is this. It gets converted into carbon dioxide, a gas, goes from a physical thing that I can hold to a gas which I can't hold and I can't smell. And it gets converted into water, but so hot water, it's steam. And so what happens is the mass of the log gets converted into two gases. Where does that mass go? Up the chimney. I did not destroy the log. I converted it into something, and the mass went up into the air. But people didn't see it, so they didn't know about it. And so there was a misconception. But when we looked at this, this is what happens. Whatever you start with, the amount of weight and stuff at the beginning must be accounted for, the weight and the mass and the stuff in the products. And so we just cannot have an equation. What we have to have is a balanced equation. We have to account for everything on both sides for you to tell a true chemical story. If you don't get this right, the whole thing falls apart. And so in this case, you can see we draw out the reaction in the case where we have one carbon that's black with 4 hydrogens attached to it. We'd write it like this. 2 oxygens, we'd write it like this, creates carbon dioxide and 2 waters. And you can count. There are 4 hydrogens. There's 1 carbon. There are 4 oxygens on both sides. This is why we have to put a coefficient of 2 here and a coefficient of 2 there for this to be a true chemical story. So balancing equations is very important. And so if I take a look at this, the following diagram represents a chemical reaction. All right? The red spheres are oxygen and the blue spheres are nitrogen. Write a chemical formula for the reactant and the products. What would be the chemical formula for the reactants? What are the things that are reacting? Looking at that picture. There are 2 things. All right? What are the 2 things? Oxygen, and that would be written as what? O what? O2 plus what else is floating around at the beginning? What is blue? Nitrogen, and is attached to what at the beginning? An oxygen. So how many to how many? 1 to 1. Will yield. What do we end up at the end? 2 oxygens per nitrogen. So the product would be a nitrogen and 2. Okay? So those are what's reacting. There's O2 and NOs, and it'll produce NO2. So nitrogen monoxide plus oxygen will make what? Name that other. Nitrogen what? The product is dioxide. Oh, naming again. Oh, we're never going to get away from it. It's going to haunt you. Now, is this a true chemical story that I have told you? No. Okay. What in the world is wrong with this story? It's not balanced. Okay. And so I will show you how I'm going to balance this. I will tell you how I think about it in just a little bit. Now look at my reaction. How many nitrogens are on this side, represented here? 2. How many nitrogens? 2. How many oxygens are represented here, the way I have written this? 4. How many here? 2. And how many here? 2 plus 2 is? Oh, get out your iPhones. We'll get this done. So everything is balanced. All right. Now, does the picture represent a balanced equation? It does. If you physically counted each of those little spheres, the number of oxygens are same on both sides. The number of nitrogens are the same on both sides. And so, yes, the number are equal. Okay? And so we can think about it in picture form. We can think about it in the equation form. But what you really need to make sure is that at the beginning and at the end, every atom is represented. Now, look at the picture. There's lots of atoms, right? And if I count, there are 1, 2, 3, 4, 5, 6, 7, 8 nitrogen oxides, nitrogen monoxides. And there are 1, 2, 3, 4 oxygens. I did not show you exactly how many were in there when I did the equation. I showed you the least common denominator or the lowest ratios, okay? Because we can't actually count how many are in a container. And so we show the equations in the smallest ratio that we can, okay? And so to balance an equation, you're going to be given, at the minimum, the reactants. I may ask you to predict the products. At this moment in time, I will not, because I haven't told you how to predict products. But give me a moment. I'll give you some things that you're going to have to predict, okay? Predict the products if possible, if you have to, okay? And then here's the key. Balance each one of the atoms one at a time, okay? And this is how you do it. You look at both sides and you decide which side has the largest amount of that atom. That will make your decision why you need to change the other side. So for each time, you look at each atom and you decide which one has the largest number. And then you try to make the other side that same number. But do it for each atom, not for groups, because that can take you down the road. It'll work 80% of the time. But if you do each atom individually, that'll work 100% of the time. Okay? The other thing, if you can help it, have oxygen the very last atom. Oxygen can take you down roads you don't want to go. Okay? So try to do oxygen very last. And if you can help it, keep hydrogen second to last. That usually helps you. Every so often you have to violate that rule, but keeping those to last is probably the best option if you can. And so a very simple thing that you would look at, if I look at this equation up here, okay, this one, I've got reactants, there I've got products. The first thing I look at is the non-oxygen and non-hydrogen compound, and I have a carbon here and one carbon there. Uh-oh, 1 and 1. I'm all balanced, right? Is that perfectly balanced? The carbon is. Is the whole thing balanced? No. Okay, check this out. Hydrogens, how many? How many over here? 2. This one is why I'm going to do something to this side. I have 4 on the reactants. How can I make 4 on the products? What can I put in coefficient? 2. That has a consequence, doesn't it? When I put a 2 in front of the hydrogen, what do I also affect? The oxygen. Okay? On this side, how many oxygens do I have? On this side, how many oxygens right here? 2. Plus how many right here? Another 2. 2 plus 2 is 4. I got 4 oxygens over here. How do I make that 4? Put a 2 there. Okay? Do you think I'm going to put something like this on the test? Maybe on the test. Will I put like something like this on CHEM-111? It's going to be a little harder. Okay, I'm going to show you some things that'll happen when we get into problems, because that looks too easy. Okay, looking at a very easy one again. Sodium, sodium, water, sodium hydroxide, hydrogen. Okay, you saw it balanced, but let's take a look. This side, sodium, I've got 1, correct? This side, how many? 1. Okay. Hydrogens, I have how many here? 2. And I have how many here? 1 there and 2 there. Uh-oh. Think about this. I have 3 hydrogens on this side, right? That's more, correct? If I put numbers in front of this, can I ever get an odd number? No. I have to go up by evens on here, okay? This is 3. All right, here's my choice. I've got to make this side even. What is the easiest way to make this side even so that I can make the hydrogens even on this side? What could I do? If you put an even number in front of here, like this, 2, okay, that changes things up. How many hydrogens do I have now? 2 plus 2 is 4, right? Can I put something here? Yeah, 2. Now, that 2 had a consequence. It did affect this hydrogen. What else did it affect? The oxygen and the sodium. Uh-oh, I had already done sodium, right? I changed sodium. So what do I have to do on this side? I have to put a 2 because the sodium is 2 on the product side. All right, now, how many oxygens do I have? It's the last thing, right? On this side I have how many? 2. On this side I have how many? Oh, that's too simple. Let's try this one. Okay, what do I look at first? I can look at iron first, yep. And that's what I truly want you to do. But since this is very, very simple, look at the oxygen real quick. One side has how many? This side has how many? How many does this one have? Uh-oh, we've got an issue of odds and evens again. I can only change this by evens. This is only odd. What is the simplest way to make this one even? Let's put a 2 in front of this. Okay. All right. If that is true, I have how many oxygens on this side? 6. How many here? Only 2. Can I make this side 6? By putting a what? Good. All right. I've done oxygen, but I still have to finish out iron. How many here? How many here? 1. Can I make this 4? By putting a... When you look at this, after you finish, remember, small whole number ratio, can you reduce that at all? No. So this is a good one. All right. Let's try, I don't know, let's try the carbons. How many here? How many here? 1. This is the decider. How can I make this 2? Put a 2. Great. All right. Now what do we have? Hydrogen. How many here? 4. How many here? 2. What do I put in front of it? Great. Okay. Last thing I need to do is oxygen. How many here? 4. How many here? 2. 2 plus 4 is 6. Can I put something here? Yes. What can I put? 3. Okay. Let's make this just slightly more complicated. Okay. These all worked out real well. I haven't gotten to you a point where you have to go, oh, now what do I do? Let's get to that point. So I'm going to make something up, and I'm going to hope that it messes everything up. Stop. Okay. All right, let's mess everything up. Okay, I'm going to do this. C2H4O. That's a different compound. I will still add oxygen. I will still make CO2, and I will still make water. That doesn't look too different, does it? Okay, but it's going to have a consequence. All right. If I go and I do my same logic, 2 carbons, I need to make 2 over there. That doesn't look any different. I still have 4 hydrogens. I'm going to make 2 here to make 4 hydrogens. That doesn't look any different. Okay. And then I still look at and I say, I've got 4 there, I got 2 there, I have 6 oxygens that I have to deal with. Okay. That looks like 60, but it's 6 oxygens. Okay. All right. Now on this side, if I have 6 oxygens, this represents 1. Minus 1. I need 5 oxygens now. What can I put in front of here that will make 5? Yeah, I can't. Well, you can put 2.5, but you can't have a half oxygen. So, uh-oh, what in the world do I do now if I run into this? Okay, it did not balance. Oh, shoot, it didn't balance. So what you're going to do is you're going to start over. This is where doing chemistry in pencil is good. Okay. When you started this, this is what you assumed, and you didn't know you were doing this. You assumed you had one of these because this is the first thing you made your decision. You said you had 2 carbons. Okay? If one doesn't work, you do this. 2. Okay? And we go again. And if we go through it and it doesn't work out, what do? You start back at the first one and you put what in front of it? 3. And if that doesn't work, you go back and put a 4. And if 4 doesn't work, you put a 5. 5 doesn't work, a 6. If you start getting up 6, 7, 8, 9, 10, something might be screwy. Okay? You might need then to check your entire work to make sure your compounds are right. Usually they're small whole number, usually under 10. Okay? All right, but this has a consequence. How many carbons now? 4. I can make 4 on this side because it had 1 by putting a 4 in front of it. All right? Now how many hydrogens do I have? 8. On this side, I can make 8, stop, by putting a 4 in front of it, correct? All right. Now, on this side, I have 2 oxygens plus 2. I have 4 oxygens on this side. On this side, I have how many oxygens? 8. There. And then how many oxygens here? 4 equals 12. 12 on this side. How many oxygens here again? 2. Minus 2, I got 10. What can I put here to make it 10? 5. So, when you get to an end and it doesn't work out, you can go back and restart at the first element or first compound you started with and double it. Okay? And go back and work that way. So, one element at a time. Oxygen and hydrogen last, and they're very, very simple. And if you get to a place that you have to start over, the first element or compound that you start making decisions, double that, and then triple that, and then quadruple that until you finish out. I won't be so nice all the time. Sometimes I will give you words instead of an equation. And so solid aluminum reacts with a solution of hydrochloric acid to form aqueous aluminum chloride and hydrogen gas. Okay, other than crying, what do I do? Okay, what is the first thing that is reacting? Aluminum. What kind of aluminum did it say? Solid. Aluminum, not with anything else, is the element aluminum. Plus hydrochloric acid. Oh, Damien's coming back. What's hydrochloric acid? HCl. And it is a solution, so that is aqueous. Yields aluminum chloride. So I've got to do some scratch work now. Stop it. Okay. So it was aluminum solid plus HCl aqueous yields aluminum. When it reacts, becomes a +3. Oh, did you remember that? Chlorine, when it reacts, becomes a -1. And 3 and 1 doesn't balance out directly, so crisscross. Aluminum, Cl3. And hydrogen gas is what? H2, one of the diatomics. And we said it was a gas. And I have a balanced equation. Yes? No, I do not have a balanced equation. All right. Okay. We're going to have all kinds of problems. Where do you want to start with? Aluminum, 1 and 1. Good.
Start with chlorine.
Okay, chlorine. Which one has the most? Products or reactants? The reactants or the products? Chlorine, I have 3 here. Chlorine, I have 1 there. Can I make this 3? Yes. by putting a 3. That's great. Now hydrogen. What do we find about hydrogen? This side I have how many? 3. This side I have how many? 2. Uh-oh. So what do? I start over.
In front of the H2.
Yes.
The H2.
We started with AlCl3 as the first decider, and we said we had one of those. Well, now I go back and I put 2. That has consequences. I now have 2 aluminums on this side, right? How do I make this 2? Put a 2. Okay. Now, I have how many chlorines? I have 6 total. How do I make this 6? Put a 6. And now I have on this side how many hydrogens? 6. How many here? 2. Can I make it 6? Can I reduce that at all? No. Okay. And so, how do you know if you can balance an equation? You got to do so. Okay? Now, you need to follow a pattern. You need to do it one at a time. Do one at a time to solve these. All right. At this moment in time, I told you the entire chemical story except for the balancing part. But I said that sometimes you're going to have to predict products. Here are the kinds of reactions that you're going to have to predict. Okay? The reaction, oh man, this looks all messy, doesn't it? Here is the big deal. If I take a metal and I plop it in water, okay, a lot of times the reaction will produce 2 things. Hydrogen gas and the metal hydroxide. So I give a general reaction that says a metal, that is solid, plus water, that is liquid, will yield whatever that metal ion is bound to hydroxide, that will be aqueous, and hydrogen gas. Here's the key. What metals do this? Group 1 and Group 2. Alkali and alkaline earth metals do this. Okay? So, I could now tell you sodium and water react. Balance the equation. You would predict what actually happens. All right? A combination reaction. 2 or more items to react products. Combination means there are more reactants than there are products. There are less number of products than reactants. So 2 things can come to 1, 3 things can go to 2. In this case, the element magnesium and the element oxygen produce the compound. Name that compound. Magnesium oxide. Okay, that's a combination. A decomposition meant something fell apart. Okay, you may not be able to predict this one, but you could classify this one. Sodium azide, that is what the compound is. We'll break into sodium and 3 nitrogens. Interesting thing, sodium azide is actually a poison. It is more poisonous than sodium cyanide. Okay? But you sit within 3 feet of this or a foot of this every day if you drive a car because it is in airbags. The sodium azide is converted upon a crash using electricity into a gas, nitrogen, that inflates the airbag. And so a poison is being used to protect you. Combination, combustion in air. This is one that you would need to know and you can predict. If you take a hydrocarbon, this is a compound that has either carbon and hydrogen alone or carbon, hydrogen, and oxygen. Okay, a compound that has those atoms, and you combust it, meaning you add oxygen. Another name for combustion is burning. Burning is just adding oxygen. You will produce two things, carbon dioxide and water. Okay? And so, you can predict the outcome of any combustion of a hydrocarbon producing CO2 and H2O. Okay, the metathesis reaction. All right? This is what I like to call the Lee-Pedmol reaction. Okay, watch this. Guy A is going with girl X at the beginning of the week. And guy B is going with girl Y at the beginning of the week. But by the end of the week, guy A is now going with girl Y, and guy B is now going with girl X, and hopefully X and Y are not roommates, because that would complicate it up a little bit. Okay? A metathesis reaction is an exchange. You may have also heard it as double displacement or double replacement, where the cation will go with this anion and this cation will go with this anion in exchange. Okay? They'll switch up. Also, there's a single replacement where girl X could switch from guy A to guy B, and you can have a single replacement reaction. So, double replacement, single replacement reactions can occur. Now, there are reasons why metathesis reactions occur, and it's called the driving force. What drives you to do this reaction? Just because I mix two things in a test tube, why would actually occur? The first is to form a precipitate. When two solutions that are clear are put together, they can form a solid. And if a solid is formed, the reaction goes. I haven't told you how to predict that yet. I will later. Second, I can produce a non or a weak electrolyte. The most often production of an electrolyte that you'll see is the production of water, liquid water. The only other liquid that you will predict right now is if you make mercury metal, that's a liquid. Water is the other liquid that you will predict right now. And the last, formation of a gas. Hydrogen sulfide is a gas. Hydrogen sulfide is the smell of rotten eggs. You will do an experiment and produce hydrogen sulfide in the laboratory. But if you produce a gas, CO2, hydrogen gas, oxygen gas, hydrogen sulfide, that will be the reason why that metathesis exchange actually occurs. Okay. Here, this one you already know, but you didn't know you knew. A metal and a nonmetal form a salt. We have called the salt an ionic compound. An ionic compound, in general, chemists call it a salt. Everybody outside this building calls what salt? Sodium chloride. That's the metal, sodium, and the non-metal, chlorine, reacting to make sodium chloride. That is salts are much more general. If you put metal oxides in water, they tend to be basic. We'll come back to this. Know that definition, but you don't have to understand why. When we tend to put non-metal oxides into water, they become acidic. Know the definition. We'll get into acids and bases later in much more detail. I'm not exactly sure why they put that on the slides. Alkali metals. Oxygen, if you have to predict, okay, we form the oxide, oxygen 2-. That is what you would predict. But there are other ways that oxygen can actually react. It can make a peroxide. And that's a different group altogether. It's two oxygens that have -2 charge. Totally different. And then you can react and become a superoxide where O2 has a 1 minus charge. All right, what do I need you to know about this? If you predict oxygen will react with something, you assume O2 minus. Okay? If you're given a name that has peroxide in it, then you use the anion shown. And if you're given a name superoxide, use the anion shown. I would have to tell you the name for you to know that is the ion that you use. Both the peroxide and the superoxide are polyatomic ions. Okay, so they have their own name. They are a group. And so you can only know that it becomes that if I give you that in the name. The alkaline earth metals form that metal hydroxide, but it's interesting. All of the alkali metals will do the reaction. But if you look at the alkali metals, only the ones at the bottom do it very well. You actually have to react magnesium with steam, water with energy for it to react that way, and beryllium, you can't even get it to react. So most of the alkaline earth metals create the metal hydroxide.